Nino's leaky faucet. Where does he come up with these?
All right, thank you for joining our OC STEM webinar today. Today we have David Giannis from Rocket Science Tutors and Jolie McLean as well, who's a UCI graduate student. Today they'll be talking about the engineering design process and also to let you know a little bit about themselves and what Rocket Science Tutors does, and to help you connect with them to help you support your students in your programs and to find out more information about what they do. So today, I'd like to introduce Mr. David Giannis and Jolie.
Well, thanks, Roy. This is Dave Janish. Just wanted to say that Jolie and I really appreciate the opportunity to be on this webinar today and tell you a little bit about Rocket Science Tutors and about how real-life engineering happens in middle schools and high schools as well. Nino Polizzi is our CEO. He was intending to be here today. Unfortunately, he could not get away from his job as a teacher at the academy here in Santa Ana. So we'll carry the ball for him, and hopefully this will be an interesting webinar for our attendees. See, I can't get this to move here. Sorry, just 1 second. There we go. Okay, so our founding fathers, Thomas Jefferson, realized a long time ago when our nation was young that we needed to be as bright and smart as we could, and the countries that advanced the most and had the best standards of living were those who really advanced their technologies, and science, engineering, technology, and math, STEM education is where we're focusing, and nothing's changed in a few hundred years. It's an interesting graphic here, but just shows you high school is the big fat pipe and 4 million students in 9th grade. And then you go through a series of reductions here in the flow rate and going into graduating from high school, going into college, going into STEM careers. Eventually you get this little trickle that comes out the other end trying to fill the cup. So you see only 100+ thousand out of the 4 million actually graduate into a science, engineering, technology, math career. Well, our objective at Rocket Science is to go all the way up in the pipe here and get involved early on and see what we can do to fill up that cup a little bit further. So a lot of organizations spend a lot of time crafting a mission statement and try to say succinctly in 1 or 2 sentences exactly what they're trying to do. In the case of Rocket Science, we've spent quite a bit of time doing that, and our mission is very simply stated. We want to ensure America's technological future by generating interest in STEM through real-world examples in a sustained classroom environment with an all-volunteer corps of engineers and scientists. And that's exactly what we've been doing now for, we're in our 10th year. So Rocket Science Tutors, basically I like to think of us as kind of the content providers. So STEM is getting to be kind of a buzzword these days. We've been using it for the last 10 years, but lately in the last couple of years it's really taken on a lot of momentum, and here in Orange County and across the country there's been a lot of emphasis on putting this this community in place. So we like to think of ourselves as the content providers that basically have what this network needs. So to the extent we can participate, we're looking to grow and participate however we can. We're all volunteer workforce. Typically we like to do a 24-week after-school program in a school. So we're there every week for the students in a very small instructor-to-student ratio. So students are learning from the people who have done it. The emphasis on design, build, and test, which we're going to talk about today. Currently operating at 4 middle schools and 1 high school in Santa Ana, and providing over 1,000 contact hours the last school year, and conducting an annual trip to UC Irvine engineering labs where the students get to turn the dials on some of the equipment in the lab, and graduated over 500 students through the Rocket Science Tutors program to date. So what RST does is, as I mentioned, is really to ignite student interest in STEM, demonstrate these real-life applications, and reinforce math and science link, because typically you may not see that until you're in physics classes and into college, when you see how the one relates to the other and it finally all starts to make sense. We try to show that to very young students. Expose them to technical careers, create this link with the UC Irvine graduate students, provide experience building things, hands-on, using the scientific method, and encourage collaboration among the students, and always be able to speak and write and use their communication skills among themselves. So today we were asked or invited in to talk about the engineering process, and the engineering process is a very simple concept. However, students really probably are not typically taught this way as part of their normal math class, their normal science class, but as you look at what it is, it's really a simple concept where you want to create something. So as part of that, you have to define exactly what the problem is that you're trying to solve, what it is you want to create. You have to gather information and analyze possible solutions to the challenge that you have in front of you. I don't really like calling it a problem. I rather call it a challenge. Design, sketch out some examples, brainstorm. Engineers are always surrounded by whiteboards. They're always writing their ideas on a whiteboard and kind of arguing with each other about the best approach. And then once the group settles on something, go out and try to design it, test it, see if it worked, and if it didn't work, figure out a better way to make it, or figure out if it did work, how it could be improved even more on the next product or the next design that you're going to do. So as we start to expose students to this way of thinking early on in Rocket Science Tutors, it becomes second nature. Okay, so we've really emphasized process-based learning. It really is what engineering is. Much of classroom learning is not done this way, where students are hands-on and do design, build, and test. And the bridge design is kind of an excellent example of this type of process where students are learning hands-on. And this is what RST is all about, and there's, as many of you know, is a big movement in education right now to go in this direction. So I'm going to introduce Jolie here to take it from here. She's actually working in McFadden School in Santa Ana right now, and she's in the middle of this bridge project, which she's done now for a number of years. And I just want to say a bit more about her. She's a PhD candidate in biomedical engineering, and she works very closely with the students, and she's a fine example of a woman in engineering, and she is able to provide that example for the students as well. So, Jolie?
Yeah, thank you. That was a wonderful introduction. Said everything I was going to say. So I'm Jolie McLean. I'm a fourth-year PhD student at UC Irvine, and I've been working with RST at McFadden for 4 years now. So we're actually working on the bridge design project right now, and what we hope to accomplish with the whole bridge building is to expose the students to an engineering, the real engineering process and a real-life experience. And so what the students do is they actually design their own bridge. They learn about the different types of bridges, and specifically we're working on TRUSS, and they're actually building it using balsa wood, and then they test their bridge to the point of failure. And then after, they get to analyze the bridge and learn from their design. How can they improve upon their design? So real-life engineering, the students actually get to gain experience with a simulated engineering problem. And so first of all, they get to design their own bridge within certain requirements. And that's nice because they get to learn about limitations, like different materials to use or design constraints, and to work within those. And then understand the loads on the design. So they actually get to learn, about how much their bridge can actually hold, and just the capabilities of their own bridge. They get to actually build their design of the bridge. So they get to start it from concept to a complete model. And then during the testing phase, they test the bridge until it fails. And afterwards, they get to calculate the efficiency of their actual design. And so their efficiency is based on how much their bridge can actually hold and the weight of their actual bridge. And then at the very end, we get to analyze the failure and suggest redesigns of how they can actually improve. So they're always learning. It's not just a one-time event. They get to think about the future and how they can improve for next time, just like a real engineering model. And so in our bridge experiments, we start them off with an intro to bridges. We talk about bridges and what they're used for and what they're capable of. They learn a lot of different math behind bridges, like the sum of forces. They learn about truss structures and how they're so good and how they're under compression and tension. And so they get to learn about, the balance of forces and the equations behind bridges. It's also, they get to design their own bridge, which is fun for them because they get to bring out their creative aspects, and they also get to use what they just learned about the truss structures. They can kind of integrate their own creativity plus everything that they just learned. And so their engineering drawings, they also do engineering drawings where they project a 3D bridge into a 2D paper. So a lot of them, they have this spatial visual aspect that they're learning as well. Some it comes easy, some of them they kind of have to work for it, and we get to teach them how to visualize something, a 3D object in a sheet of paper. And then they get to follow the fabrication instructions, so they're actually making their own bridge. They have balsa wood and some cutters and glue, and they're constructing their bridge based on their design. And once their bridge is completed, they actually get to test until the bridge fails, which is always fun and exciting to have some load, that anticipation of breaking, and it's a nice friendly competition. And then the analysis of their failure. They get to look at the joints, where the bridge snapped, where the bridge actually failed, so we can learn about the compression and tension and the distribution of forces throughout the bridge. So here's an example of the different types of bridges that we give them. So these are all truss structures. The truss is the triangle shape, which dissipates the forces throughout because of the X and Y component in the triangle. And so we give them some examples. We encourage them, though, not to follow one of these examples, but to create their own bridge, because then they're not just strictly following something, they're becoming their own person, they're making their own bridge. This is their own design. They can even, name it the Jolie Bridge or their own bridge, which is exciting for them, especially come day of testing. So here's an example of the projecting the 3D view into a drawing on a sheet of paper. And so we give them a piece of wood as well, so they can see the front side, what you would look at the bridge from a side view, like if you're in the water under the Golden Gate Bridge, kind of looking at that side view. And then also projecting out the top view, so as if you were in an airplane looking down on the bridge. How does that look? And then also as, a passenger on a car driving through the bridge would be the right side. So you kind of really visualize every side of the bridge, not just one side or a 2D depiction of it. So you're really using your spatial skills and taking that 3D bridge and breaking it down into a 2D image. We bring a truss demo as well to kind of visualize the dissipation of forces in the truss structures. If you look at setup number 1, there's a square in the center, and when we add a force, like in image 2, you can see that the square structure, it doesn't dissipate the forces. So it's getting pulled down, in the Y direction, it is getting pulled down. It's not distributing those forces. But just simply by adding a crossbar in number 3, you're creating that truss structure, and what that's doing is it's spreading the forces throughout the bridge. So it's a nice visual representation of actually showing the students you really want these truss, the triangle structures, or else your bridge is going to fail. So it's teaching them about spreading the forces, and some places are always under compression while other areas are under tension because of the distribution of forces. And so here's just some structural analysis of what we're actually teaching, so the breakdown of forces in the X and Y component and why the truss structures are so important. Another big thing to note is the sum of forces on a bridge should always equal 0. And we always just reinforce that if the sum of forces is not equal to 0, then that is when your bridge is failing. Okay, so here is the bridge fabrication. So on the piece of paper is their actual design. That would be their 3-view drawing that they initially created, the projecting the 3D image onto a piece of paper. And they're actually building up from their own design. So they get about 10 pieces of balsa wood. So that's another constraint. They're limited on materials. They can't draw a line, every millimeter apart, because that's not realistic. And especially in the engineering world, you need to have applications that will actually work. So we are teaching them, constraints of materials, just kind of how to think in the real world. And so they're actually cutting these pieces of wood, and they're setting them down on their design, so on their drawings, and then gluing them together. So they're building one side of the bridge at a time, and they'll use pins just to hold it in place. Instead of having to hold it with your own fingers, you can use the pins to hold it down. And sometimes the students don't quite get that. So it's a lot of just explaining, it's like a replacement for your fingers to hold it down. And so this is, they kind of learn, the engineering does take time. You have to be neat, you have to be accurate, use cutters to cut every angle correctly. And this really, it helps them build. They use their hands, they get to learn hands-on. So construction details, this is what an example of a bridge would look like. So you can see, there's the front side, the right side, and the top side all built together. So this would be an example of after their bridge design. And you can see all the different faces. And this is all built from that 2D image, from the design on a piece of paper. So this is after the experiment. I think there's a slide later, but there's an object that has to fit inside the bridge, which kind of almost represents, people traveling through the bridge. You need to have these design constraints and different requirements. But this is what a bridge would look like after the testing. And so you can see the points of failure, and it was at the joints. And so you can see where the weaknesses are within the bridge. And then we would talk with the students about, okay, how can we build a better bridge next time? Like, what can you do? And a lot of times we'll bring up, different materials, a stronger material than balsa wood, or a different design, different sort of glue, different so they have the same strengths, or more or less glue in certain areas. We want to focus, too, on if they had like a big square in the center, then we would talk about their design and how they can improve their design for next time. And we'll tell them about the truss structures and make sure they really understand the distribution of forces throughout their design. So here's some really nice images of the actual testing day. And the testing day is always exciting. It's loud. They're wearing glasses. You have these weights, so you stick up in the top left, you can see the piece that goes inside the bridge, and then we hang a bucket from there, and we add weights. And so we keep adding weights until the bridge actually fails and collapses to the floor. So it's always exciting if it's your bridge there, just hoping that it doesn't break. You want to win.
It's like Mythbusters.
Yeah, the excitement's there. It's loud when it drops. Everyone kind of jumps and gets excited. Depending on how many students there are, we'll have about 2 testing sites going on at a time. And so you can see, before it's broken, you can see, on the bottom right, bottom left, you can see a constructed bridge, and then in the bottom center, you can see a student actually building his bridge before the testing phase, and you can see some designing going on in these images. They're all excited, and the energy is very high on this day. So here is with 11th grade students as well. You can see some nice representation of the design process and the testing and the building phases. We also, in the bottom left, here's a Connects bridge that we'll use as demos. Sometimes we bring a couple demos just in the beginning to keep excitement high and help visualize what the students are learning. So they are graded on this design process at the very end. So we, we come up with a problem, we design it, we build it, and we test it, and then we analyze the failure and the successes of the bridges, and we also give them a grade. So the big thing, 75%, is the design efficiency, and so that's the load at failure. So how much mass your bridge can actually hold before it breaks, before it fails. And then divided by the mass of the bridge itself. And so you want that ratio to be very, very high. You want your bridge to be very light, but to be able to hold a lot of weights. That's built to requirements. That's another thing, kind of the constraints, the size requirements. If you build, and that's kind of a real-life application, right? If you have a 30-foot gap to make a bridge, you can't make it 20 feet. That's obviously too short and it's not going to work. And you don't want to make it 100 feet just because it's excessive, it's long. The width and height requirements, if you're having cars go over this, you need to have it big enough so that a car can fit. You don't want it too big. So we talk about a lot of those size requirements and kind of bring it to real-life applications. As an engineer, what are the things that you have to think of when you're actually building? And so if they meet the requirements, they get 15% of their grade, just to make sure that they're in a realistic world. And then workmanship, just how good it looks. You don't want it to be sloppy, glue everywhere. That'll also, decrease other points, like in your efficiency and everything. But neatness of cuts, like you should, as an engineer, you should be thinking, you should be doing things precisely. You don't want to make mistakes because this is just a bridge out of balsa wood, but as a real engineer, if you are sloppy, you could make big problems that cost a lot of money. So we always kind of want to bring them back into the real world and give them examples of things that can happen and make sure that the workmanship is good. That's 10%. So here's what it looks like, the actual load testing experiment. So we get creative, we put things on top of tables, you can see the chairs over there. On the left, I think those are bookcases that the bridge is spanning. So that's supposed to be, the ravine or whatever underneath, the canyon, the water that your bridge has to cross. And so we'll make that, a certain length, which is just a little bit smaller than your bridge. And inside the bridge is the device that actually connects to the bucket. And in the bucket, you can see we have the big silver washers. We just stick them in to the bucket just very carefully. We even have more weight. So students can add, if they think their bridge is really good, they can add a lot of weight up front and then slowly add smaller amounts of weight. And then we'll hold it just maybe a couple inches off the floor, so when it actually fails, you can see it's a big, you can see that when it actually fails. So you're kind of getting creative. You can see one of the volunteers adding weights in. So here's another example. You can see inside the device that actually has to fit in there. I know one of the requirements is you have to be able to fit a block through the bridge. That's kind of a representation of cars and everything that has to pass through the bridge. So again, kind of that real-life experience to make sure that they're designing, the actual engineering process that needs to work, needs to be real. Here's kind of the workmanship as well. You can see an example on the right of a good clean cut that will be strong. There will be a lot of glue. There's a lot of area, a lot of interface between the two joints. That'd be an example of good workmanship. And then on the left, it's not mitered, so it's a weak joint. There's not a lot of area of interaction. You'd have to use a lot of glue. And so that's a lot. We also say the workmanship has to do with the strength of your bridge as well, because on the left there's going to be a weak joint. That's an example of bad workmanship. On the right, the example of good workmanship. It's a much stronger joint. So workmanship actually really pays off in terms of the strength of your bridge. And so it takes time to actually carefully miter together these joints. That's real for all engineering examples. I always tell my undergrads, even in lab, like, take extra time to do it, because if you don't, you're going to mess up and take more time. And I'll tell the students that too, like, take the time the first time around. Okay, so just a little summary about what we've done and what RST is all about. The bridge design and the build test has been proven. So we've done that for years to come now. It's a long process. It's about a 5 or 6 week process, and the students actually do a real life engineering problem. And during that, the 5 to 6 weeks, it's really exposing the students to the engineering process. They have a design from start to finish. They design their own project, they build it, and then they test it and analyze it for failure. And that's exactly what we would do in a real engineering situation. And then throughout, we're using math and science. So we're really connecting the math and physics and the engineering equations behind the entire phenomenon. So we're really trying to make that math and science connection. And not even with the bridge experiment. We do this a lot. We always teach about simple machines and the relationship between forces and distances in maybe like a catapult or fun examples. We'll build them with connects and have simple equations. The students will figure out how far something will move. And then it gives the students a chance to build something. I know if you're sitting in a classroom, it's really easy to doze off or get bored or your mind starts wandering. But I think when the students are actually using their hands and they're building something, they're much more likely to be engaged. It could be something they're interested in. They like cutting, they like gluing, they like putting it together. We also have labs like we make polymers, and it's gooey, it feels good. The students like to play with it and pretend like if they just sneezed it or something. So they get to get creative with it. And then also, especially in the bridge example, it's competition with classmates. Competition is always exciting. You and your best friend, like you have a competition, who's going to do the better bridge. It makes them more likely to have better workmanship, to have a better design, and to really, think of things in a more dynamic way. The one thing that's really cool is the students really are shocked at how strong the truss structure is. They always think that the design efficiency, which is the load at failure over the mass of the bridge, they always think it's going to be like 10 or something really small. They think that the bridge will maybe hold about the same weight or a couple times as many weight as the bridge, but it's a lot more. And depending on the bridge, I mean, it can be thousands of times. It can be a lot stronger. And so they're always just really shocked. They don't realize how good their bridges are. And so at the end, we really build their confidence and let them know like how good of a bridge they actually design. They think they get to leave on a high note, like, oh wow, like I didn't realize I was capable of creating something that strong. And so at the end of the day, we really want to promote them being engineers, and hopefully they'll get excited and think they can do science engineering. All right.
Well, I think we want to open up for questions.
Yes. So we actually have 2 questions so far. So the first question was, what does your 24-week after-school program consist of?
Yeah, so a lot of different things. I mentioned the bridge testing itself is about 5 to 6 weeks. We also do a long portion on simple machines. We probably do about 4 or 5 weeks on first class, second class, third class levers. We teach the relationship between forces and distances and just simple mechanics. For a couple weeks, we learn, I briefly mentioned, we do like a polymer lab. We learn about polymers and they actually make their own silly putty. That's really fun, that's interesting. We learn about density, so we have a bunch of different fluids like water, corn syrup, and then we have like pieces of wood or aluminum, and we watch where they float and where they sink and learn about densities. We also, obviously we're RST, Rocket Science Tutors, so at the very end of the year we build rockets. That's a couple-week program, and we actually shoot off these rockets at the end of the year.
So what would it take for a school or an after-school program themselves to get in touch with you guys, and how does that work in terms of getting you guys to be able to run this program at a school site?
Do you know?
Well, I mean, you can contact, probably Nino is the best person, or any of us that are involved. We are limited only in, we're not limited really by number of volunteers. We have a lot of volunteers, primarily retired aerospace engineers who have that time of day, and graduate students from UCI. We even have some undergraduate students on occasion. So we have the volunteers. It's just really a question of how we scale our operation to go to more and more schools, and that's our challenge today. So we're becoming more involved in organizations such as OC STEM and looking for ways to grow our footprint and be able to take programs like this to as many schools as possible. So please contact us and we'll see what we can do.
Yeah, I think Nino's information is on the front page. He's the CEO, he's the head. If you contact him, he'll be so excited. He's very enthusiastic about RST.
All right. So we have several great questions coming in as well. So the next question is, what if I don't have a degree in engineering? How can I do this?
Well, let's see. Certainly it's going to be easier if you have a degree in engineering, but there are aspects of this that non-engineers can learn just as the students learn, and will be able to teach lessons in this area. It is a bit challenging for a non-engineering person. However, there are ways to do that, and that we can overcome. I mean, there's nothing like having somebody with 20 or 30 years of engineering experience in the classroom. However, it's not always required.
We have, I mean, at every school there's a teacher that helps out as well, and that teacher might not necessarily have a degree in engineering. They might be teaching a science class or a math class at the school, so they have some background knowledge, and they're definitely able to help out.
We have another great question is, how can this activity be modified for 4th to 6th graders in an after-school program? So I guess they noticed a lot of it was with the 8th graders and then maybe with the high school students. How can this be achieved with the lower grade students?
I know some of the labs would be very easy to do. Like I mentioned, the polymers and the density labs. Those are very fun. It's kind of mixing ratios together and adding things, and it's very hands-on. You kind of feel what's going on. Some of the labs can be very easily implemented into a 4th grade or so, and you can just change a little bit about what you teach. Even polymer, I think 4th graders could get it with visual aids and everything, and plastics and giving examples. Some of them might be a little more difficult. Like I know the whole bridge building in particular. Even at the 8th grade level, schools were just worried about cutters and things like that since they are doing things by hand. For 4th graders, it might be harder, but I think they could at least get the design portion of it. I think students, even at 4th grade, they're very creative, and you can teach them maybe just not so in-depth.
I think our inspiration in Rocket Science Tutors has always been to capture students in middle school. Just about the time math starts to get difficult, they're taking algebra and they're thinking, this is really confusing and I'm not sure what good it is for me. I think I'll do something easier. that's when we like to come in and show them things like this, where they start to see, oh, this is why it's useful, and kind of capture them at that point. But we can simplify the lessons down to younger students. We can also make them a bit more complex for high school students. It's just a matter of adjusting to their particular learning abilities.
Have you guys ever been able to make a bridge strictly using popsicle sticks and glue? And how do you work around the portion where you have to cut, or can you? How would you work around that?
So we actually use popsicle sticks in the very beginning to show the truss structure. We use popsicle sticks, but they also have nuts and bolts, and so we stick them together and we put them into a square at first, and then we apply a force and just push it down with your finger and show that the square falls down. And then we do a triangle and we apply an external force, push it with your finger, and show that it's a lot stronger. And that is just a popsicle stick. And I think, yeah, maybe instead of using balsa wood and cutting it, I think you might be limited on your design, because the popsicle sticks are kind of all the same size, or pre-made sizes. But I think that could definitely work, at least
to get the idea.
Yeah.
To get this conceptual idea of how it would work. Another question is this program replicated anywhere else in the state that you know of? So you are currently present in Orange County, but are you restricted just to Orange County? But do you also know of other programs out there like yourselves throughout the state?
Yeah, there are some other programs. I ran into a gentleman from the state of Michigan, and they've been operating for 20 or 30 years in some of the inner cities in Detroit, and they're sending engineers and graduate students into the classroom, and I think they're probably a bit farther along than Rocket Science Tutors. So we had a nice discussion at the Discovery Science Center a week or so ago. But there are other groups. I don't know if you know of any specifically.
I know a lot of like summer camps. There's like fab camps. There's a big STEM one. It's in New York and Orange County. I forget the name of it right now. I know there's like summer camps that focus on STEM education. But RST is nice because it's all throughout the school year. It's not just a summer program. It's once a week, after school, and so it is a continual process. That's nice.
People are asking about Nino's contact info, so they were not able to see it anywhere. Do you know what? Do you have what his email contact would be, or for them to see that?
Oh, I think it's just delete. Yeah, here, let me.
It's on the very first slide. We can jump back.
Yeah, I think the computer's just a little delayed.
Alright, so while we look that up so that people can get his contact info, what is the budget in regards to materials for bridge building? Are those materials entirely provided by RST?
Yeah, so they're entirely provided by RST. I do every single lab with the students, but I have to admit I'm really not there for the logistics. I just show up and do what Nino tells me to do pretty much. But what we do is I'm a lead at McFadden, and Nino gives us a kit every year. And I know the budget, I can't give you an actual number, but there's limitations on balsa wood. So we have the balsa wood, we have glue. We just purchased scales for the better accuracy of actually weighing out the bridges. We have cutters. I know were one of the big expenses. Cutters for every school, and we have the boards and pieces of paper, the construction paper, the graph paper.
So the expense does not come directly. The schools themselves do not need to provide or pay for anything. You guys provide all those materials.
Yeah, up to this point, our supporters have been paying for those. Schools have not, and there's a budget for to put the program on the entire school year, and there's also a budget, specific to bridge building. So Nino will be able to answer all those questions. And I did manage to get to the first slide here, and there is his contact information.
And did you say each project was approximately 12 weeks?
No, not each project. Some projects are just one class long, so the hour or hour and a half. Like I mentioned, like the density and the polymer lab. Those are just for one class period. But the bridge building, it is like a 5 or 6 week, just depending on how quickly the students can go. But we'll do that, once a week, every week for 5 to 6 weeks.
And so I guess this leads to the next question is, what amount of time daily during that 12 weeks would you estimate? So is that pretty much every class is an hour and a half?
Yeah, we do hour and a half once a week. So it's an after-school program, 1 day a week.
I think you said it would be possible to have an RST lead a project with a group of students. Is this correct?
Yeah, like a one-time project or a weekly project.
Could you clarify for us the question? Now go on to the next question real quick. Do you guys only stay in Orange County specifically, or do you reach out to other counties as well?
Well, up to this point, our focus has been in Orange County and specific to the Santa Ana School District. But we've had inquiries from Los Angeles County and other areas. It's really just a matter of scaling for us because the program it will be the same. So someone who wants to participate and kind of learn about the program could certainly take it to another county or even another state.
I guess it's ongoing. So you guys would be there strictly to lead the whole program. So in terms of leading the project, you would be the ongoing lead throughout the whole time. Duration.
Yeah, like I go to McFadden once a week. I do Mondays. And so we get there, we bring all of our materials, we pull everything out. I teach the course. There is a teacher there. She takes role and kind of, the administrator for the classroom. But I am the main person. Like I teach the lesson, and then we have volunteers that go around and we work with the students hands-on. And, a couple of students at a time. And then at the end, we'll wrap up and kind of make sure, ask questions and see what the students have learned, really make sure they understood the core concepts that we wanted to teach that day. And then, we take all of our supplies and we pack up. So it is all us coming to you guys, teaching this lesson, and then coming back next week.
Oh, that's great. Are there any other questions? So how many students can be in a lesson? In a group, or how do you guys have limitations on sizes?
So a lot of it depends on the school. I'm at McFadden, and it's actually the biggest school that we have right now. It's about 25 to 30 students. Some of the other schools I know have maybe like a dozen or less, depending on the day, of students that come in. And so I think one year we did have about 50 students, and I think we preferred a little bit smaller. It was great. It was a great problem to have too many students interested in RST. But I think it did get a little chaotic, and what we were worried about is that there wasn't enough tutor interaction with those students. We like to keep a small ratio. So if one RST member has 10 students to work with, we prefer it to be smaller. We'd like 5 or less.
But that there again is where teachers can really come in, because if you have a combination of the engineer volunteers and some teachers, you could be very effective.
Mm-hmm.
And so I asked this question earlier, but I just want to reiterate for the group is, how can students get involved in your program? How does that work?
Students like at UC Irvine?
Students at the school site. How do they get into being part of this project with RST at a school site?
So I know the school advertises it. And I think I'm working at an 8th grade level, and so I know they come and if it's signed something, the parents have to sign a waiver.
And it's completely free for them.
It's promoted in the schools, and we actually have a little trick. Jolie mentioned at the end of the school year, they launch rockets. It builds to a crescendo, and that's kind of the big thing. And these are the chemical rockets. I mean, it's a big deal. And they take measurements and they do analysis. But if say it's an 8th grade class, get the 7th graders out there to watch the rocket launches. Of course, they all point to it and say, hey, I'm going to do that next year. So it's a little bit of advertising to the next crop. So.
All right, these are great questions. Are there any more questions from the audience that you would like to ask?
I just have one point. I want to hit home that at the end of the year, so we do the rockets as well, and then after the rocket segment, maybe like in June, the end of their school year, we actually have the students come to UC Irvine as well, and we set up demos in our lab. Like we'll have a laser show, or people work with like non-Newtonian fluids, and they'll have it on a speaker so you can see like it stiffening up as song with lots of bass or something, so you're applying external force. I know students are really excited about that. It's awesome they get to come and see lab grade, like a university, all the expensive equipment that's going on. They get to look at like their own skin cells and stuff. And it's really cool for them. So they kind of get to see what's beyond the 8th grade level. So we teach them these tools throughout the year, these math and engineering concepts. And then at the very end, they kind of get to see like, oh wow, university is really cool. I want to go there one day. And it kind of inspires them to keep working and build their math and science skills.
So we have another great question coming in is, do the students work mostly with worksheets to fill out the data, or can you elaborate more on the reflection writing component of the program?
Yeah, we give them worksheets. We always have a tutor there with them, working with them one-on-one, kind of building. But we do ask them questions, and we want them to answer, incomplete sentences, incomplete thoughts, because, as, the grad student in biomedical engineering, my whole job is to publish papers. And so I'm constantly writing. If you're a professor, you're constantly writing grants. You always need to communicate your science. And so we really try to emphasize that communication is huge. You have to write down your findings in a way that people understand.
And the other thing is neatness. In the very beginning of the program, quite a bit of emphasis is spent on being neat and detailed, because engineers are known to be neat and detailed, and really it's the only way they can keep track of sometimes a lot of very extensive and detailed data and analysis. So that's emphasized strongly in the beginning and then throughout the program.
Yeah, I've even brought in my lab notebook, and I've showed them, because there are so many rules to a scientific lab notebook, and I'll even let them know, like, I've known people that have missed out on patents because they were sloppy and they didn't document things, and they didn't, get their signatures, write down dates, or just document things. And so we really do stress the importance. Like, you need to be neat, you need to clarify everything, and communicate very well.
How do you help them translate the engineering design process to other applications or for other subjects? Do you help them make that connection of using the thought process, basically?
I think we'll throw out a lot of examples just throughout, depending on whatever we're working on. I'll ask them to, because we don't, I might not quite know what lesson they're learning in their 8th grade science class, so I'll kind of ask questions and probe where they are, and if they've learned about it, then kind of connect.
So, and just for a point of clarification, you do focus strictly 6 to 12, is that right? Or have you worked in a middle school elementary school environment at any point? Or do you try to keep it within that middle school?
Our target's been the middle school, but there's been some one-off programs that have occurred on weekends and things that are for the younger kids as well.
So it would be possible to facilitate a program for the younger kids?
It would definitely be possible to do something for the younger students as well, sure.
And so do you know how low you have gone before? Has it, if it's been with 4th graders or 5th graders, possibly?
I don't know. That's probably a Nino question.
Yeah.
All right.
We've done everything.
So he would be the primary contact that everybody can reach out to.
Yeah. Nino is the creator of ours.
He's the inspiration behind RST, and he's now teaching at the academy in Santa Ana, and he's taking all these same ideas and he's implementing them in a high school environment. But certainly they can translate up to high school. They can translate down to elementary school.
Just a quick question: have you guys ever, in any circumstance, somehow, maybe you weren't the ones to completely lead a project, but somehow facilitated and supported an existing after-school program? Do you think that's something that may be possible?
Yeah, it's definitely possible. I mean, I'm actually on the board of RST. I don't volunteer in the classroom, but business development is something I'm helping the group with, and so that could mean a partnership with someone who wants to work with us in the classroom, in another after-school program. It can mean a lot of different things. So definitely contact Nino, and I can get involved with that as well.
Well, thank you so much. So are there any other questions out there? Great questions. Are you able to share who some of your supporters are? with Rocket Science Tutors?
Yeah, we have, I can't remember them all. I believe they're on the website, but there's like Wells Fargo and who's the cable company? It's Time Warner Cable. There's a number of funders. It's just they're not all coming to me right now, but I think that we've got them listed on the website somewhere, if I'm not mistaken. Oh, the Weingart Group is another one.
All right, these are all great questions. So if there's any more questions, I'd like to leave the floor open for a few more. You'd be willing before the webinar, before we end the webinar. Do you know what it takes to, do you know Vino has conversations with the school districts themselves, or does it all pretty much work at the site level with the school principal?
Well, I know we have to get everything cleared through the school district. Like I know just for me to be on campus, my driver's license, everything has to be cleared. In terms of as the whole, do you know more about that?
Yeah, RST is trying to branch out a bit by working not just with the school district, but with the Orange County Department of Ed and the Orange County STEM Initiative and other networks beyond a particular school district. But certainly our focus has been in the Santa Ana schools for now the 10th year.
What was the website to your Rocket Science Tutors? What was the website address?
Oh, it's www.rocketsciencetutors.com.
Yeah. I was just looking at questions.
All right, these are all great questions. So if we don't have any more questions, I'd like to thank again Juliet and Joe for spending your time with us and being able to share a little bit about who you are and letting people aware of the great work that you guys are doing out there and really talking about what it looks like out there to actually implement an engineering class or an engineering, teaching the engineering design concept as well, because I know for myself and for a lot of our other programs, it is actually very difficult to try to teach an engineering class and not even knowing where to start. So have you guys also, just one question like this is, have you guys done anything in terms of just consulting with programs at this time?
A little bit, and we certainly like to do more, and I think that's one of the big benefits of you having invited us in to do this webinar. So thank you so much, Roy, for the opportunity, and to the folks that are on there looking at this today, please get in contact with us. We're very open to working with after-school programs, with the schools, with the STEM initiative.
All right. So if there's no more questions, I'd really like to thank everybody again for coming and spending your morning with us, an hour with us, and I hope you all have a good day, and please be careful on the road because it is wet today. So everyone, thank you very much. Have a good day.
Thank you. Bye.
Go! Thank you. You did good. Oh, are we still on?
So open.